So welcome to the next lecture of microwave engineering. So we were discussing the first unit, which is about the planar waveguides. So till now we have discussed the introduction part, which is the electromagnetic spectrum and the various bands of microwaves. And then we covered what is a waveguide and what is the general structure of planar waveguide. And then we discussed what are the different modes that can exist in a planar waveguide based on the polarization. So, right, we discussed that whenever we launch a parallel polarized wave into the waveguide, we will get a wave which is having a magnetic field that is always perpendicular to to the direction of propagation. So, such a mode is called as transverse magnetic mode, right? And then, whenever we launch a vertically polarized wave into the waveguide, so we get Ez as 0, that is electric field is always transverse to the direction of propagation. So such a wave is called as TE wave. Okay, and we had discussed a special case that whenever a parallel polarized wave is launched at an angle of 90 degrees with respect to the plane of incidence, so we get a special wave which is called as TEM wave, transverse electric and magnetic wave. That is, both electric field and magnetic field will have uh, will have only transverse components, that is Ez and Hz, both of them are 0. Okay, so this TEM wave has a special property that it travels as a lossless wave inside the waveguide. So the waveguide acts as an unbounded media, okay, or a free space media. Okay, so this we discussed in the previous class. Now in this lecture, let us discuss the next topic, which is about the general analysis of wave propagation, general analysis of wave propagation, general analysis of wave propagation in waveguides. Okay, so the next topic that we are going to discuss is about the general analysis of wave propagation in waveguides. Okay, so you can also rename this topic as the determination of field components inside the waveguide. Okay, inside the waveguide. So right inside a waveguide, any waveguide, that can be planar waveguide or a rectangular waveguide or a circular waveguide, any waveguide. So we will be doing the general analysis. That means we will be deriving the expressions for field components like Ex, Ey, Ez, Hx, Hy, Hz. Okay, their expressions we will derive, okay, here, right? And these expressions, they are valid for any kind of waveguide. Okay, so we are not deriving with respect to planar waveguide or rectangular waveguide. Okay, so that is why we named it as general analysis, right? So let us see this. Okay, so for this, let us first take up a setup. So let us assume I have a waveguide of some arbitrary shape. Okay, not necessarily rectangular or circular or planar, anything. So let us take a general waveguide of some arbitrary structure. Now, in this waveguide, I have two directions that are of importance. We discussed this earlier also. So one direction, okay, which is along the dimensions of the waveguide, or along the right length of the waveguide, which is called as a longitudinal direction. Longitudinal direction, and the direction that is perpendicular to this longitudinal directions are called as the transverse directions, isn't it? Okay, so transverse directions, right? So longitudinal direction is the direction which is along the length of the waveguide, and transverse direction is the directions that are perpendicular to the longitudinal directions. Okay, let us assume that the waveguide is placed such a way that the longitudinal direction is along the z-axis, okay, and the transverse directions are along x and y axis. Okay, so let us assume that right in our waveguide, the longitudinal direction refers to z-axis and the right transverse directions refers to x and y axis. Okay, so this is the assumption that we make. Okay, right. Now assuming a rectangular coordinate system, okay, a rectangular coordinate system, we have the field components. So electric field E bar will have three components. So we can write that it as Ex into Ax plus Ey into Ay plus Ez into Az. So it is having component along x-axis, component along y-axis, and component along z-axis. Okay. So in this case, this Ez into Az is called as a longitudinal component, and Ex and Ey, Ex into Ax and Ey into Ey is called as the transverse component. This is a longitudinal component and this is the transverse component. Okay. Similarly, right, we can also write, okay, the magnetic field, right, okay, as components, or a combination of, okay, all the three components like this. Okay, hx into ax, hy into ay, and hz into az. Sorry, az. So again here also this is the longitudinal component and these two are the transverse component. So magnetic field and electric field we are writing in the form of, right, longitudinal and transverse components. Okay, right. Now here, now the next thing is, so right, our idea here, right, our idea here is to right, this general analysis is basically, these are the electric field components E bar and H bar representations in the free space. Okay, in the free space we will have all the, right, the electric field having a components of Ex, Ey, and Ez. Similarly, magnetic field also has Hx, Hy, and Hz. Okay, now our idea here is, so what is this derivation is all about is, so to determine these values, to determine the value of Ex, Ey, Ez, Hx, Hy, Hz inside a waveguide. Okay, inside a waveguide. So what is going to happen to these components? So what are the expressions for these components is what we are going to derive now. Okay, so this general analysis is basically the determination of these components Ex, Ey, Ez, Hx, Hy, Hz inside the waveguide. Okay, we are going to derive the expressions for these components inside the waveguide, which is what we are calling it as general analysis of the wave propagation in the waveguide. Okay, so let us derive those components. Yeah. So firstly, right. So okay. So for this, we will start with Maxwell's equations. So we have a Maxwell's equation which is given by del cross E bar is equal to, del cross E is equal to, right, J omega mu into H bar, isn't it? So del cross E is equal to J omega mu into H bar. This is a Maxwell's equation. So from this Maxwell's equation, right, I can write del cross E. E here is represented as Ex Ax plus Ey Ay plus Ez Az is equal to J omega mu into, right, H can be written as Hx Ax plus Hy Ay plus Hz Az. Okay, so this is the thing, right? Now now del is a vector, so it is generally represented as dou by dou x of ax plus dou by dou y of ay plus dou by dou z of az. Okay, so del, right, and this is a vector. So these two are vectors. So we have to take a cross product of these two, so which can be given as, the cross product is ax, ay, az. Okay, so here I will get the dou terms, which is dou by dou x, dou by dou y, and dou by dou z. Okay, then the next terms ex, ey, and ez. Okay, is equal to, right, here I write it as j omega mu into, so same thing, hx ax plus hy ay plus hz az. Okay, right. Now let us take the cross product of this. So the first term will be, right, so I have to multiply these two. So dou by dou y of Ez minus, okay, dou by dou z of Ey into Ax. Okay, that is the first term. Next term I will get it as minus Ay into, what are the components I will get? Dou by dou x of Ez minus dou by dou z of Ex. Okay, so that is what I will get, right? Next, okay, the next term that I'm going to get is plus, okay, Az into, what is that I'm going to get? Az into, so this term, so dou by dou x of Ey minus, okay, dou by dou y of Ex. Okay, so this is the right expansion of this cross product is equal to right. So here j omega mu into hx ax plus j omega mu into hy ay. Okay, plus j omega mu into hz az. Okay, so these are the components that I'm going to get, isn't it? Yeah. Okay. So, yeah, sorry, a small correction. So here I get a minus sign. So, right, a negative sign. Yeah. So, all these components will get a negative sign. Okay. Yes. Sorry. So, small correction. So, del cross E bar is equal to minus j omega mu into H bar. So, which I get like this. Okay. Right. So, this is the thing. Now, yeah. Now, right, let us equate. Okay, on both sides we have ax terms, ay terms, right, and az term. So let us individually right, equate them. Okay, so firstly equating the ax terms, so what I get, so dou ez by dou y, okay, minus dou ey by dou z is equal to, so here I get minus j omega mu into hx. So this is one, right? Then next, equating the y terms, so ay terms, so dou ez by dou x minus dou ex by dou z is equal to, right, so because it is a negative and here also negative, so we'll cancel that out, so I'll get it as j omega mu into hy. Okay, clear with this? Yeah. Next, next equating the az terms, so right, the az terms is dou ex by, okay, dou, sorry, yeah, dou ey by dou x minus dou ex by dou y is equal to, right, what I get is minus j omega mu into, okay, what is the other term that I will get as hz. Okay, so this is the expressions for yeah, so these are the expressions for, right, the three wave components that I get. Okay, so equating from this, expansion, if I equate the individual terms, right, I will get like this. So let these three as equation one, this entire set as equation one. So what I have done, simple, what I have done is I have taken the first Maxwell's equation, which is del cross E bar is equal to minus j omega mu into H bar. So using this, right, substituted E is equal to EXAX, EYAY, EZAZ, and H is equal to HXAX plus HYAY plus HZAZ. Okay, I have substituted them, right, and I have equated the, right, AX terms on both sides, AY terms, and AZ terms. So I got this equation. Okay, yeah. So put this equation aside for some time. Okay, right. So okay, this, I think this is, till this point it is clear, right? Now let us take the other Maxwell's equation. So which is, right, let us take the other Maxwell equation. So which is del cross H bar is equal to j omega epsilon into E bar. Okay, so let us take the Maxwell's equation that comes from inconsistency of Ampere's law. So if I take that equation, so I get del cross H bar is equal to j omega epsilon into E bar. So from this Maxwell's equation, again substituting, del cross H bar can be written as hxax plus hyay plus hzaz is equal to j omega epsilon into E bar can be written as exax plus eyay plus ezaz. Okay, right. So okay, this is the expansion. So instead of H bar, I have written HXAX, HYAY, HZAZ, and instead of E bar, I have written EXAX, EYAY, EZAZ. Okay, right. Now similar, because del is right, again dou by dou x of AX, dou by dou y of AY, plus dou by dou z of AZ. Okay, so right, taking the cross product of the two, so AX ay, az, dou by dou x, dou by dou y, dou by dou z. Okay, and this is hx, hy, hz is equal to, right, what we got? We got the same thing, j omega epsilon into ex ax plus ey ay plus ez az. Okay, yeah, so this is what I get, isn't it? Yeah. Now let us expand this cross product. So firstly, ax term, on this side I have ax. So ax into, so what is that I'm going to get? Dou by dou y into hz, okay, minus dou by dou z into hy, okay, right? Next, minus ay into what is this? I'm going to get ay into, okay, so if I take this out, dou by dou x of hz minus dou by dou z of hx, okay. Next, plus az into the third term. What is the third term? I'm going to get dou hz by dou x, okay, minus dou hz by dou x minus, sorry, okay, yeah, sorry, dou hy by dou x, okay, minus dou hx by dou y, okay. So cross multiplication of these two rows, okay, so this into this and this into this is equal to, so expanding this also, j omega epsilon into ex ax plus j omega epsilon into ey ay plus j omega epsilon into ez az. Okay, so I'll get right the expansion like this. Okay, so right, simple. So I have taken this Maxwell's equation, del cross h bar is equal to j omega epsilon into e bar. Now h bar can be written as hx into ax, hy into ay, hz into az, and e bar can be written as ex into ax plus ey into ay plus az into az. Okay, now this is a cross product of the two terms del and this. So I've taken the cross product. Okay, I have written like this. Now what we do is, let us do the same thing. Compare the ax, ay, az terms on both the sides and let us write the expressions. Okay, so what I get. Okay, so comparing ax expressions, so what I get is dou hz by dou y minus dou hy by dou z is equal to, right, j omega epsilon into ex. Okay, so that is the first term. Then next, second term, what is the second term I get? So this is the second term, right? So dou by dou x, dou hz by dou x minus dou hx by dou z is equal to minus j omega epsilon into ey. This is what I'm going to get. Okay, next the third term that I'm going to get is, so equating these two, so dou hy by dou x minus dou hx by dou y is equal to j omega epsilon into, sorry, ez. Okay, so right, let this three equations set as the equation 2. Okay, so the second equation. Okay, so right, so comparing ax terms on both sides, ay terms on both sides, and az terms on both sides, we will get the three equations like this. Okay, right. So okay, till this I think it is clear. So I have taken the two Maxwell's equations, and from those two equations I have substituted e bar and h bar in both cases, and right, separated the ax terms, ay terms, and az terms. Okay, right. Now from the first equation, okay, from the equation 1, from equation 1, let us take equation 1. From equation 1 we can write the value of, okay, hy. Okay, so what is that we got for hy? So looking at the second equation of that equation 1, the second equation of that equation 1, so what I get is, okay, so hy is equal to, right, 1 by j omega mu, 1 by j omega mu into, right, what is that I'm going to get? Okay, because it is hy, so dou by dou x of right, hz minus dou by dou z of hx. Okay, so this is what we will get, right? Sorry, this or ex, sorry, This is Ex and this is Ez and this is X. Okay, yeah. So looking at the second equation for us will be Hy is equal to so 1 by j omega mu into dou by dou x of Ez minus dou by dou z of Ex. Okay, so this one. Okay, correct. Now now substitute this equation, substitute this let's say this is the third equation, substitute this in the Ex term. Okay, substitute that in the Ex term of this equation. Okay, yeah, so substitute this Hy in Ex, substitute Hy in Ex. Okay, yeah, so let us do that, right? So let us see what we will get. Okay, yes, so Hy is from the equation 1, we'll get Hy as, right, we got something like this: dou by dou x of Ez minus dou by dou z of Ex is equal to j omega mu into Hy. So from that I've just changed the simple structure. Hy is equal to 1 by j omega mu into dou by dou x of Ez minus dou by dou z of Ex. Okay, right, now I want to substitute this Hy here. Okay, here, right? Okay, in the Ex term. Okay, so firstly, this is my equation. From this, Ex can be written as Ex is equal to 1 by, okay, or we'll just keep that as it is, j omega epsilon into Ex is equal to, okay, so dou Hz by dou y, this is unchanged, we'll write it as it is. Now dou by dou z of instead of Hy, let us substitute this term. So 1 by j omega mu into, right, what is that I'm going to get? Dou Ez by dou x, okay, minus dou Ex by dou, okay. So understood? So instead of Hy, okay, I have a Hy term. So instead of this Hy, I'm writing like this. Okay, yeah, clear with this? So Hy, I got this. So I'm substituting that here, right? Now, now j omega epsilon into Ex is equal to dou Hz by dou y. The first term doesn't get any change. Now let us expand this. So first minus dou by dou z of, okay, into 1 by j omega mu, right, into dou Ez by dou x. Okay, so this is the first term of this. Next, second term, minus of minus will become plus. Okay, 1 by j omega mu, right, into dou square by dou z square of Ex, isn't it? So same thing. Okay, right. Okay, so when I expand this, I will get something like this. Now what I do is, so here I have a Ex term, here also I have a Ex term. Okay, so let us take this Ex term to this side, okay, and take that as common. Ex into, so first term is j omega epsilon, which remains as it is, right, minus 1 by j omega mu into dou square by dou z square, okay, into Ex is equal to, so what is the left out term? Dou Hz by dou y minus 1 by j omega mu into dou by dou z, dou by dou x of Ez. Okay, so this is what is remaining, right? Okay, this is the equation that I get. Okay, now here I'm assuming, let us assume that dou by dou z is equal to minus gamma. Okay, so this is not right unknown assumption. It is very known to us when we derive the wave equation of EM theory. In EM theory also, we let dou by dou z is equal to minus gamma. So let us assume dou by dou z is equal to minus gamma, which is here gamma represents the propagation constant. Okay, so dou by dou z is equal to minus gamma. So from that, okay, dou square by dou z square, that is dou square by dou z square is equal to gamma square. Okay, is equal to gamma square. And there dou z by dou z into dou z by dou z minus gamma into minus gamma, which is nothing but gamma square. Okay, yeah. So let dou by dou z is equal to minus gamma and dou square z by dou z square is equal to gamma square. Okay, yeah, so substitute that here. So Ex into j omega epsilon minus 1 by j omega mu into what is dou square by gamma by dou square, right? Dou square by dou z square is gamma square, okay, is equal to, right? So on this side, so first term will remain as it is, dou hz by dou y minus 1 by j omega mu into, so dou by dou z I am writing it as gamma into dou by dou x will remain as it is into Ez. Clear with this? So what we are doing is we are substituting dou by dou z as minus gamma and dou square by dou z square as gamma square. So this is minus gamma. Okay, right? So minus gamma, instead of dou by dou z I write minus gamma. Instead of dou square by dou z square I am writing gamma square. Okay, so I got this. Okay, so clear this point, right? I have taken, right? We have taken started with the Maxwell's equations. We got the expressions for, right, Ex, Ey, Ez, Hx, Hy, Hz. So again we have to solve out that. So for that what I am doing is I am taking the right value of Hy and substituting that in Ex. Okay, so I get, right, like this. So Ex, in place of Ex I am writing this term. Okay, and I am expanding that. After that, next I am assuming a small thing. What is that? Dou by dou z is equal to minus gamma and dou square by dou z square is equal to gamma square. Okay, right. Now after this, yeah. So this is the equation that I got. Yeah, let me write up everything. So this is the expression that we have got as of now. Okay, so write ex into so see here, so if I take the LCM, the denominator is j omega mu. So when I multiply j omega mu and j omega epsilon, I'll get j square omega square mu epsilon. Okay, so j square is nothing but minus 1. Okay, so when I multiply these two, what I am going to get? Minus omega square mu epsilon. Okay, minus gamma square. Okay, right? Clear with this? Okay, so when I multiply j omega mu with the j omega epsilon, what I get? J square omega square mu epsilon. J square is minus 1, omega square mu epsilon. So that's what I've written. Okay, is equal to, so here also what I do is, okay, so right, let us take 1 by j omega mu common in both the terms. Okay, right, so here there is no j omega mu, so I will get it multiplied j omega mu into dou hz by dou y minus, okay, because I have taken j omega mu common, so I will not get that again. Here I have minus gamma, here I have minus. So this will become plus into gamma divided by dou x by dou x into Ez. Okay. So this is the term that I am going to get, isn't it? Okay. So what I have done, I have taken 1 by j omega mu as common in both the terms. Here I don't have a j omega mu, 1 by j omega mu. So I'll get it multiplied. Okay. And this will become like this. So now I can cancel out j omega mu on both sides. Okay. And take minus common here, right? So minus Ex, okay, or Ex into minus of omega square mu epsilon plus gamma square, okay, that's what I have written, is equal to, right, so first I will write this term gamma by dou x of, okay, Ez, right, that's what I have, plus j omega mu into dou hz by dou y. Okay, so same thing, what I have written is like this. Okay, right, now this implies Ex is equal to minus, okay, so yeah, before this, yeah, one thing, so let us assume gamma square plus omega square mu epsilon as some constant which is equal to h square. So let gamma square plus, okay, gamma square plus omega square mu epsilon is equal to a constant value which has some importance. We will discuss that later. So let us assume that this value is equal to h square. So therefore what I get is Ex into minus h square is equal to gamma into dou Ez by dou x plus j omega mu into dou hz by dou y. This is the term I get. Okay. So from this, right, the final expression for Ex is equal to, right, minus gamma by h square into dou Ez by dou x and minus j omega mu by h square into dou hz by dou y. Okay, so right, this is the expression for Ex. Okay, Ex. Understood? So, right, what we have derived, we have taken the Maxwell's equations. From that, I got all the field components, Ex, Ey, etc. Okay, but right, so but there has been a lot of combinations. I will tell you why we are doing all this. Okay, so what is the difference between here I got an Ex expression. Earlier also I got an expression for Ex was there. Okay, so what is the difference and why we are doing all this, I will tell you, right? Okay, yeah. So next is in the similar lines, so using the same concept, so this we have done for Ex, right? So if we do the same kind of analysis for Ey, okay, Hx and Hy, so I will get the expressions as, okay, so first for Ey, right? So if I take the Ey, okay, Ey term, so this will be, right, this will be equal to minus gamma by h square into, right, so dou Ez by dou y, so same as that of this, dou Az by dou y. Next, plus j omega mu by h square, into dou hz by dou x. So instead of, right, the denominators gets reversed. Here I get dou by dou y, here I get dou by dou x. Okay. Next, Hx is equal to the expression for Hx will be equal to, so minus gamma by h square into, so this will be dou hz by dou x minus gamma by h, right, dou hz by dou x, okay, and plus j omega epsilon by h square into dou Ez by dou y. Okay, so this will be the expression for, right, the Hx term. Okay, similarly Hy is equal to minus gamma by h square into dou hz by dou y, okay, minus j omega mu by h square, j omega epsilon by h square into dou Ez by dou x. Okay, so, right, these are the expressions for Ey, Hx, Hy and Ex. Okay, so Ex, Ey, Hx, Hy. So we can derive all these other expressions also, right? All the other three terms. Okay, I have told you the derivation for Ex. In the same way, we can derive the expressions for Ey, Hx and Hy also. Okay, using the similar kind of approach. That is why I am not repeating them. So we will get the expressions like this. Okay, right. Now, yeah, now, right, okay, now let us understand it carefully. So earlier also from the Maxwell's equations also, we got the equations for Ex, Ey, Hx, Hy, okay, directly. But why again we are manipulating them? So see here, whenever I am solving, I hope this is done. Yeah. So whenever we are solving for, whenever we want to find out the expressions for the field terms or the field components inside a waveguide, the general approach, right, we follow is, okay, so we will first determine the components Ez and Hz, which are called as the longitudinal components or the wave components, the components in the direction of the wave, okay, wave direction, isn't it? So we assume if this is my waveguide, so there are two directions. One is the direction along the longitudinal component. So this is the direction of the wave propagation. Okay. So, right, whenever we want to solve for the right field components inside of any waveguide, the general approach is first we will solve for the components that are present or that are available on the direction of the propagation, that is longitudinal direction. Okay, so those are nothing but Ez and Hz. So once I know these two components, so okay, then I can calculate, because these are easy to calculate without any knowledge, with just the knowledge of boundary conditions and the mode of propagation, we can find out Ez and Hz. Okay, so we will find out Ez and Hz. After that, using them, we can calculate the other terms. So right, if I know these components, then I can calculate Hx, Hy, right, Ex and Ey components, which are the transverse components. Okay, so right, so this is the general approach. Therefore, so if you look at the first equations that we derived from the Maxwell's equations, that is equation 1 and 2, okay, one, the set that we derived, the three equations of 1 and the three equations of the 2. So there we have the values of Ex, Ey, Ez and also Hx, Hy, Hz. But those values, right, okay, if I take for example Ex, this has, right, the components of Hz and there is a component of Hz and there is a component of Hy, isn't it? So right, in the calculation of Ex, I have a component of Hz and I have a component of Hy. So again, Hy is a transverse component. Okay, so I don't know that, right? Again, if I want to calculate Hy, right, I need an information regarding Ez, right, Ez, okay, and H. Sorry. So here again I need a component, right, the information regarding Ex and Hz. Okay. So in this case also, right, Ex is not known to me. Okay. So all of them are interdependent, right? So right, all of them have transverse components also. Okay. Therefore, it is very difficult to calculate them directly. That is the reason why. So by substituting in one another, we have got now Hx, Hy, Ex, Ey all having components. Okay, all of them are expressed only in terms of longitudinal components, that is Ez and Hz. Okay, and the equations అన్నిటిని కూడా we have reframed such that the Hx, Hy, Ex, Ey ఈ అన్నిటి కూడా, these are all expressed only in terms of Ez and Hz. Okay, because the general approach that we follow is we will first calculate Ez and Hz and then we will calculate the right remaining terms. Okay, so that is the right thing. Okay, so right, okay, so till now, right, we have calculated the four components. Okay, what are the four components that we calculated? Ex, Ey, Ez, Ex, Ey, Hx and Hy. So all these are expressed in terms of Hz and Ez. Okay, now what are the expressions for Ez and Hz? How do we calculate Ez and Hz? Okay, yeah, so for this okay, let us go back to the basic equation of the wave, which is expressed or which is given by the Hertz. Okay, which is called as the Helmholtz equation, the Helmholtz equation. So which is given by, okay, so right, if because the wave is propagating, let us assume the wave propagation is in z direction. Okay, so because that's what we have assumed, right? So because the wave propagation in z direction, so therefore the wave components will be expressed as, okay, for electric field, for the E field, the component will be del square Ez is equal to, right, omega square mu epsilon minus omega square, okay, mu epsilon into, right, Ez. Okay, and similarly for H field, for the magnetic field, we get the equation del square Hz is equal to omega square mu epsilon Hz. Okay, so these are the two equations which are called as the Helmholtz equation or the wave equations. Okay, the wave equations or the Hertz equations. Okay, so from these equations we can calculate, okay, from these equations we can calculate the expressions for Ez and Hz. Okay, how? Let us see. Okay, so we know that, let us take this first equation. Okay, let us take the first equation, which is del square Ez is equal to minus omega square into mu epsilon into Ez. Okay, so from this equation, del square is nothing but, because it is a Cartesian coordinate system, we can write it as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, so therefore del square Ez is equal to dou square Ez by dou x square plus dou square Ez by dou y square plus dou square Ez by, okay, dou z square, right? Dou z square, which is again equal to omega minus omega square into mu epsilon into Ez. Okay, right? This is the thing. Okay. Now, assuming dou square by dou z square is equal to gamma square. Okay. So, dou square by dou z square is equal to gamma square. So, let us substitute that here. So, we will get dou square by dou x square into Ez. Okay. Plus dou square Ez by dou y square. Here gamma square into Ez is equal to minus omega square mu epsilon into Ez. Okay. So what I have assumed? I have assumed dou by dou z square, dou square by dou z square is equal to gamma square. Okay. So this is the equation that I have. Now from this, right? From this, so remaining dou square by dou x square into Ez plus, okay, dou square by dou y square into Ez. Okay, let us bring this term also here. So what I get, plus omega square mu epsilon, so gamma square plus omega square mu epsilon into Ez is equal to 0. Okay, yeah. So we have assumed that this value, right, gamma square plus omega square mu epsilon is basically assumed as a constant called as h square. Okay, so therefore, right, so I will get the equation as dou square Ez by dou x square plus dou square Ez by dou y square plus h square Ez is equal to 0. So this is my, right, equation, a quadratic partial derivative equation which I can solve for Ez, right, and using the boundary conditions I can derive all the constants, okay, from which I can calculate the Ez value. Okay, so this is one equation, right? In the similar lines, if I take the second equation, okay, if I take the second equation, so and solve for it, so then I'll get dou square hz by dou x square plus dou square hz by dou y square plus small h square into hz is equal to 0. So this right equation, okay, so let this equations be 4. Okay, so these two equations, okay, right, are simple partial derivative equations, partial differential equations. So by using the concept of variation, separation of variables or any other partial derivative solution technique, we can find out the values of Ez and H. Okay, right? So okay, so right, with this our general analysis is completed, right? So using these set of equations, right, as I told you, the procedure from now onwards, right, if I want to analysis, okay, if I want to analyze any waveguide or the proper wave propagation inside a waveguide, for any waveguide, for any mode, whatever may be the waveguide, whatever may be the wave, right, wave, we can use these equations and we can do it. Okay, so firstly what I do is, okay, the procedure how to do the analysis is, first take the general equations of, right, take the general equations of Ez and Hz. Okay, so we will take the general expressions for Ez and Hz. Okay, so in this expression, right, substitute the given conditions, substitute the given, right, conditions, okay, and apply the boundary conditions, then apply the boundary conditions, okay, boundary conditions, and solve for Ez and Hz. Okay, so we'll have to get the solution for Ez and Hz. So once I get the solution for Ez and Hz, so using those two values, we can determine all the other values of Ex, Ey, Hx, Hy using the above equations. Okay, so that is the reason why this derivation is a very important concept, because all the other waveguides, right, the wave propagation inside any waveguide, okay, and inside and any mode, we can do the same thing, right? So this is called as the general analysis or the framework for calculating the, right, field expressions inside the waveguide. Okay, So I hope that this concept is very clear, right? So in the next coming sessions, we will be calculating, right, using this general analysis, we will be calculating the field expressions, right, inside the waveguides. Okay. Firstly, in the first unit, we will be solving that for planar waveguide. So for a planar waveguide, for each mode, okay, we have three modes. Yesterday we discussed, in the previous lecture we discussed TE mode, TM mode, and TEM mode. So for each mode, okay, we will be deriving what are the field expressions inside the waveguide, and from that, okay, what are the characteristics of the waves, right, will also be discussed. Okay. So right, this general analysis of the waveguide equations is very important. Okay, this general framework is the starting point for the analysis of any waveguide. Okay, so I hope this lecture is understood.